Okay. So I believe we are not forgetting our objectives, right? Our objective is to basically develop a model, right, that can predict the IC50 concentration. IC50 is the required concentration to inhibit half percentage of a protein. So what you are trying to do now is we are trying to predict the IC50, like the potency, let me put it that way in the simple term, of a drug against a particular disease. And in this model, our disease we are focusing on is TB, Mycobacterium tuberculosis. So we are trying to build a model that can predict for us if a new drug can inhibit or can stop Mycobacterium tuberculosis from developing, right? And what you are trying to do is to go on existing data, right? Experimental data that has already used experimental data that already have different drugs, right? At least in this data we are working on, we have about 1,200 drugs that has been tested on tuberculosis, right? And they have their IC50 calculated. So what we are trying to do now is we are trying to extract information from the structure of the drugs, of each of the drugs, over 1,200 drugs. We are extracting the information from them, right? And we want to correlate their informations to their IC50, their bioactivity values. So, and we all know biologically the functional group or the structure of the drug is responsible for its bioactivity. So what we are trying to do is, what are the functional group? What are the chemical structure of these compounds? And how does this chemical structure correlate with their bioactivity, their IC50? So that is what we are trying to do. And we are trying to train our model that, okay, if you see this structure, maybe 5 hydrogen, we're talking about the Lipinski rules. Maybe when you see a drug with IC50, let me let me go to the last data one we have. Yeah. So for instance, now I'm just trying to explain this in detail to us. Now, so this is the last data we did last week. So what we are trying to do is we are trying to extract information from the canonical smell of each drug, right? And we are trying to show that when you see a particular compound with this molecular weight, log p value of this and this number of hydrogen donor, hydrogen acceptor, right? With this attribute, this is going to give you a possible PIC 50 of 8, and that is active, right? So we are still extracting information, right, from the structure of each drugs, and we are trying to correlate them, right, with their bioactivity against Mycobacterium tuberculosis. So that is what you are trying to do. And like I've used example, many times that, for instance, when you want to predict if a particular object is a car, for instance, or a dog, or let me use dog. Let's say you are looking at what you have a picture, and you want to say, okay, this picture that I'm having, is it a dog? And if it is a dog, what type of dog is it? Caucasian? Is it German Shepherd? Is it Babu? Is it Rottweiler? I'm just using that for instance. So for you to be able to do that, you have to first of all write the attributes of each of those dogs. So for instance, when when you're comparing German Shepherd and maybe Pit Bull, German Shepherd had long hair, right? Long tail, right? A very moderate size of head, right? And a short leg at the back, right? And not that muscular. Now, if you compare that features with what you have for a pit bull has short ears, right? Very muscular, big head, right? The same length of the front legs and the back legs. So when you bring So you already trained your model that when you see these features in this dog, this is pitbull. When you see these features in this dog, this is what Rottweiler, right? Now, when you now come with a new object, a new dog, and you don't know whether this dog is pitbull or Rottweiler, when you feed in that into the model is going to look at the features you already defined, right? And say, okay, this dog you are bringing to me, what are the features? Does the features resemble that of a pitbull or a boabu? So that is what your model is going to look at, and at the end of it, it's going to say, okay, based on this model I've already been trained with, and based on the information I'm able to extract from this new object, from this new dog, okay, this dog is boabu and not pitbull, or is pitbull and not boabu. So the same approach is what we are doing here. So based on this information we are extracting from these drugs, right? And we are calling it to their bioactivity class and their PIC50. So when you come with a new drug, the model is going to examine that new drug and say, okay, these are the functional group on this new drug. Let me match it to what I have already. Does it structure correlate with any of what I have? If it correlates with you, okay, what is the IC50 of the one that I have already? And if they correlate with each of, maybe for this, then you say, okay, the IC50 of your new drug is going to be 7.2. So that is what you have been trying to do for the past for the past 2 weeks, right? And the first time we did a kind of a data extraction, right? And I said one of the database where you can have experimental data for against different diseases or against different proteins is the CHEMPO database, right? And we successfully downloaded our data for Mycobacterium tuberculosis, if you guys remember. And last week also we did what is called a exploratory data analysis, right? Whereby we try to we define the bioactivity class, and we try to convert because of values. We are trying to convert. We converted our IC50 to PIC50, right? And from there we did what is called statistical analysis. Like, okay, like what is the log P? Does the log P value of active compounds and the inactive compound, is it a non-hypotency? Is there a kind of, is it the same distribution or different distribution? So our general hypothesis is there is no difference between the log P of active and the inactive, right? But when we tested the hypothesis, we use the Mann-Whitney U-test, right? The hypothesis showed to us that there is significant difference. So there is difference, which means the log P value, the log P value, the PIC50, the molecular weight of the active drugs is different from that of the what? Inactive drugs. So in this case, we can say PIC50, sorry, log P, PIC50, molecular weight, hydrogen bond, and everything, like we've talked about, has something to do with the bioactivity, and which is good for us. So by the time you are coming up with your own drugs, right, it's going to look at all these features, right, and match them to activity. So that was what we did last week, right? So today we are going further to calculate what is called molecular descriptor, right? So molecular descriptor. So that molecular descriptor is also, we are trying to have some what is called some fingerprints, extracting some information, yes, from extract some information from the canonical smile. Yes. We still need to, apart from the Lipinski descriptor that we did, we still have to do to see what is called a padded descriptor, right? Some molecular fingerprint. So like we are still extracting on informations, from the canonical smile. So that will give us a lot of features, and that will help us to have an accurate and precise model. So like this is part three of this. So in this we'll be building a data science project, yes. And this part three will be calculating molecular descriptor that are essentially quantitative description of the compound. Like you see, last week we tried to calculate the Lipinski rule from the compound canonical smile, right? If you remember. So this time around, we are trying to calculate molecular descriptor from the compound, quantitative molecular descriptor. All this will help us to to have better understanding of the structure and the correlation with the bioactivity of each drug that we are working on. So today, before we go that, I want, because of some because of some bash script in this particular one, I don't know, I've been having issue with running the bash script on, sorry, on a typical what is it, a notepad, notebook. But today I'm going to introduce you to an important IDE. That's the Google Colab. The Google Colab is freely available on the internet. So just go to Google. That's what you are going to use today. Just go to Google Colab. Type Google Colab in your browser. Google Colab. Can you see Google Colab? Right? So you see the first one. Welcome to Collaboratory. Do you see that? And it's going to give you this page. In your own case, if you are doing it for the first time, it's going to be empty. But in my own case, I've done a lot of work on it before. Right. I've done a lot of work on it before. And the script you are going to use today, I already label it as CBB part 3. You know, we've done part 1, part 2. So we are looking at part 3, descriptor data set. So once you open your Google Colab, come to upload. You go to upload. So want to upload our script. So I'm going to send you this script at the end of even the first part, the part 1, part 2 that we did. You can run it also on this Google Colab. Yes, if you want to do, you can either use Anaconda Jupyter Notebook, or you can use Google Colab Jupyter Notebook, whichever one that is convenient for you. But I'm just showing you. Go to your browser, type Google Colab. It will give it to you, and you see welcome to Collaboratory. Colab means collaboratory. You just short it. And once you have this, you have an empty a pop-up like this, and you go to upload. So when you click on upload, then choose. So then you will choose where do you have your script, your Jupyter Notebook, your Python script. This is my here. Click on it and open. It will automatically open it for you. Right? It will open it up for you to work with. It will open it up for you to work with. So can you see? So once it opens it up for you to work with, then click on this folder. Yeah, this is your home directory. Yeah. So whatever work you are doing here, it will be saved. It will be saved on this site. It's not going to be saved on your computer. It will be saving here, right? And if you remember last time, on the part 2 that we did, the last data set that we saved is called MTB. It's called MTB underscore 05 underscore activity underscore data. So this is what you are going to work with today. So when you come to your Google Colab, it is always important for you to import. So you have to import your you have to import your you have to sorry you have to move your what is your the last data set that you'll be using for this. You have to bring it to this space. And there are 2 ways you can do that. You can go to your folder where you have it. I have it here. This is what we did last time, right? You can pick it up like this, drag it here. If you go, if you definitely move to this space. And if you can't do that, you can just click on this upload to session storage, upload. Click on it. It will take you to your local directory. Then you can navigate to where you have the document. So in this case, let me just do it here. So click on this. Is what the last data we work on last, and that is what we'll be working on today as well. Right? Open. So okay. Can you see it's already on this page? So you can either drag it here, or you use this function to upload that data set, right? So you can drag it or use that. So let me show you. You can just yeah. So you can just go there and drag it to where you want it to be, right? So now, for you to do that, now once you've dragged that, the next thing to do is we have to download the padded descriptor. Yes, the padded descriptor is available online, right? We have to download. The first thing is download the accurate activity. So yeah, the first thing is to download the padded descriptor. Already provide the access to it. So I already have this for you. Just run this script. When you run the script, it automatically downloads the padded descriptor. It's called padded.zip. Yes, padded.zip. So once you click on it, it will download it. Can you see? Already download, it's saved, right? Then after that, you click on this. So it's going to, you also download the zip and the sh script. So when you click on this, it will also download this for you. And once you do that, then we have to unzip the folder, right? Can you see it's downloaded this the two, the padded.sh, padded.z zip is already downloaded. So the next thing is to what? To unzip this. So when you unzip it, it will unzip that and it will give you that is going to run. So I want to replace. Yes. So why it's asking me that is because I already did this before. That's why it's showing me this. Yeah. So just click. So can you see it unzip everything in that folder, right? So let me run that again. I already have this script. Just run this script. So on Google Colab, just come to the line. You will see this play. Just click on it. Click on it. It will run the script. Move to the next one. I have it here. Click on this play icon. It will run that. Click on this. So as I'm clicking on this, it already zip the file, and that is why you can see all the stuff I'm doing here. So once you because you need to next thing now is to import our data set. Yes, is to import the last data set that we work on, the mtb underscore 05 underscore back 50 underscore data. If you remember, so to do that, don't forget we need to import our pandas, right? Import panda, right? And this now, because this is not on our local file, this is on the Google Colab. Can you see it here? So just let's form a new variable df3 is equals to pandas.read underscore csv in bracket, open bracket, then inverted comma. So we just put the name of the file that of the banking data that we produced from the previous from part 2. You put it here. You don't need to put part because we are not working. It's not on our laptop. It's on this Google Colab cloud stuff. So you put that, and the next thing is you run. So we've imported the data that we have here. We've imported onto our working space here, and let's look at that. So this is it. So this is what we did last week. So last week we have the symbol ID for each of the drug, the canonical SMILE, right? Bioactivity data, active, inactive. We have the molecular, the Pinsky rules. If you remember, molecular weight, log P, and number of hydrogen donors, number of hydrogen acceptors, and we have our PIC50 calculated. PIC50 calculated. So we have 1,233 drugs remaining, and we have 9 colons. Now, once that is done, don't forget the next thing the purpose of this is to calculate molecular descriptor, right? From the canonical SMILE. So to do that, we need to create a new variable called selection. So in selection, we have canonical SMILE, we have molecular chamber, right? So in that case, what we're saying now is we are creating a new variable from df3 underscore selection. So what this means is, say, go to df3 and extract canonical SMILE and chamber molecule underscore chamber underscore ID. So don't forget you already define canonical SMILE and chamber underscore ID into selection. So go to df3 and extract selection. Selection equals to canonical SMILE and chamber, and save it into a new directory called df3 underscore selection. So in this df3 underscore selection, we have only what? Only canonical SMILE and what? And chamber underscore molecule underscore chamber underscore ID. So what you are now trying to do now is we are trying to save this into our file, into our workplace. So df3 underscore, save it to, we call it molecular.smi, right? So what we have here, so this canonical smile and molecular this, we are saving it into our folder, just the way we save all those ones into our file, right? We save it, and that is what we have here. So if you look for molecule.smi, so it's going to give you, can you see, just the canonical smile, right? And the Campbell ID only. So we save the canonical smile and the what? And the Campbell ID only into molecule.smi. So this add 5 means give us the first 5, right? So this is a bash script. It's not a typical uh, Python command. That's why you can see this. So now let's see. Now we see. Don't forget, if you look at this, we see we have our 1,238 compounds, right? And by the time we look at this Campbell and canonical smile, we still have our same 1,238 compounds, because we only extract the canonical smile and the Campbell ID of those compounds. Now, once that is done, the next thing now is for us to calculate the fingerprint descriptor. So we calculate the padded descriptor. So to do that, we have to run this padded script first. Yes. And once you do that, we ask you to run. So already this molecule.smi, right? It is already included in the script. It's already included in this script. I'm telling you, it's already included in this script. So that's why anytime you are running it, it has to be molecule.smi. So when you run this bash script, it's going to run this bash script already contain this information. Let me try to show you. Let me show you that bash script. I'm coming. I don't think I have it. Let me show you bash script. That bash script. I have the bash script. Okay. Okay. Can you see the bash script? Okay. Is it even this? No, it's not. It's not. It's not here. Is just give me 1 second. I think it should be here. It should be somewhere. I don't want, because of our time. Let me just. I think that is already included. So just run that, right? So when you click on this, run it, right? Then it's going to calculate, because like I said, this molecule.smi that contains the canonical smile and the Campbell ID is already included in this script. So when you run it, it's going to calculate the padded descriptor for each of the compound. Can you see processing Campbell? Can you see for each of them is doing it? It's going to do it for the 1,238 compounds that we have in there. It's going to do that for 1,238 compounds that we have in there. So it's going to do that. It's going to calculate that. So what you are trying to do now is we are still trying to extract more molecular information from the canonical smile, because canonical smile is just talking about the functional group on the drug. So we want to match the molecular description, the what is it? The molecular description, the Lipinski descriptors, right? We want to look at how does each of these things correlate with the bioactivity and the IC50 of the drug, so that when we bring in a new, let's say we bring in a new drug like Telenor, our model is going to calculate all these things that we are calculating. Is going to calculate it for all our drugs, because it is when it calculates for our new drug, it will match it to the one that it has already, and say, okay, once I've calculated this descriptor for these new drugs and I've matched it with what I already have in my archive, then this is like to be the PIC50 or the IC50 of this particular drug that you are showing me. So by that way, if you are doing an experiment in the lab and you already have a model for a particular disease and you have a list of drugs, before you go to lab to test them, you can run those drugs on your model to predict the PIC50 or the IC50 of that drug, and the lower the IC50, or no, sorry, depending the PIC50 rather, depend on the on your model, it will predict for you whether your drug is going to be active or inactive. So can you see it's still doing it for, it's going to do it for all the compounds. Can you see it's still doing it for, so it's still is doing calculate for, we only have we are 289, 298, now 400 out of 1,238 drugs that we have. So it's going to calculate that. And once you calculate that, I'm going to show you this. Let's give it time. It's still running. So while this is running, do we have anybody that has a question? Maybe something is not clear. Can you ask, please? Any question? Or you can drop your question in the chat box. Any question or anything that is not clear? I decided to run this through for everyone. So by the time we are writing this up in like 2 weeks' time, and I'm giving you your respective drugs. Okay, you are working with coronavirus protease enzyme. You are working with this, so you will be able to know how this is running. And if you have any question, please feel free to get in touch with me or with Dr. Scott. So can you see it's still running, right? So we have 500 and 600 now out of 1238. So let's wait until it runs. And I'm going to show you that at the end of it. Yeah. So if you have any question, please feel free to ask. Any question? So we are building model. And do you know one thing about this model building? That is how model is being built for virtually everything that you use on your phone, that you use at home. Yeah. Like last time I spoke to you about, you know, when you are filling some form, they will ask you, are you SARS-CoV-2 positive? So to show whether you have been exposed, they will ask you, did you travel to hotspot area before? Have you had a contact with someone that has SARS-CoV-2? Are you coughing? Are you sneezing? Do you have headache? Do you have chest pain? All those things, these are the features, right? So when you answer yes to all of them, the model will have been built or configured that, okay, if someone is having this, is saying yes to cough, saying yes to travel to hotspots, saying yes to being close with someone that has tested positive to COVID, the model will say you are likely to be COVID positive. So it's the same approach that we are doing for this. The only difference is in this case, we are trying to extract information from the chemical structure of the drugs, right? And we are matching it to the what? To the bioactivity. So the information we are extracting from the chemical structure, they are the features. And the bioactivity, PIC50, is the what? Is the label. So that is the, so when they ask you, are you HIV, have you been to, or have you traveled to SARS-CoV-2 hotspot area? Are you coughing? Do you have headache? Do you have headache? Are you sneezing? Those are features, right? Now the label is SARS-CoV-2 positive or negative. So that's how every model is built. So you train the machine will look at, okay, these are the features of people that has SARS-CoV-2, and these are the features of people that do not have SARS-CoV-2. These are the features of compounds that are active to MTB. These are the features of compounds that are not active to MTB. So that when you come next time with a new drug, the model will calculate, we look at the features of that new drugs and match it to the already existing information you have given onto the model. Yeah, that's great. I think so. It's completed now. So, and if you look at that, so this is it now. Can you see? So we've calculated the descriptors, descriptors underscore output.csv. So now, don't forget everything that you have here is on the Google Colab data cloud, right? So there is a way you can save this directly onto your own laptop, to your own local laptop, right? And you can save it collectively, or you can save it by right-clicking on it and click download. So if I should click download on this now, it will download this particular one, can you see, onto my laptop. So let's open this and see what is there. Can you see the molecular descriptor for each of the drugs? Can you see? How many do we have here? Can you see? So all these things are what are fingerprints. So it's based on the canonical SMILE for each of those drugs. It calculated the molecular fingerprint as either 1 or 0, 1 or 0, 1 or 0. So all these things that you are seeing, they have features. They have what they mean, right? So if you see for this compound is 1, 1, this place is 0, at this point is 0, this for this compound is 1. So all those things with our already existing Lipinski rule will be the features that will be matched to the bioactivity of each drugs, right? Bioactivity of each drug. So when you come with a new drug, our model is going to calculate all these things that you are seeing again for your new drugs and match it. Okay, which already existing data drug has similar description with your new drugs, and so okay, if this is similar with this is the IC50 of this, and this is likely to be the IC50 of your new drugs. Yes, yeah. Somebody is asking Obi. They say just to be clear, the process we just went through was to create the library against which are comparing features exactly. So what you are trying to do now is we are extracting features, right, from each of the drugs. So the features will now be matched to their bioactivity. The bioactivity is the label, right? So like the example I give the other time, when you are looking at the tail, the head, the ear of the dogs, right? Those are the features. Now, the label is pit bull or bear bull, right? So in this case, all these things we are doing, we are extracting features from our drugs, right? And we are matching that features to the label, either active or inactive, PIC50 value. So that's what you are trying to do. So now the way we are now extracting the features is two ways. One, we're extracting the features using the Lipinski rule, looking at the molecular weight, the PIC50, right? The molecular weight, the PIC50, log P, the number of hydrogen donor, number of hydrogen acceptor. That's one. Another way is also we are extracting features is looking at this padded descriptor that we just did now. So at the end of it, we are still going to match the Lipinski rule and this together, right? Let's continue. Let me go back. Let's stop this. Okay. Can you guys see my screen? All right. So now we've done that. So what I just did here is to show you what I have here. So just list. So this means list. Show me what I have here. So you can see everything that I have here is what is there. Now, what is now next is now trying to train our model now, right? So we are preparing the X and the Y matrix. We are getting towards. So based on that, we are creating because this is the descriptor that we just calculated now, right? Is here. So we want to create a new variable for it. So we call it df3/x equals to pandas read CSV descriptor and save it here, right? So everything that all this descriptor stuff is now in this DS3. And that's why if you look at this df3_s, it is the same thing I opened for you in that Excel that is here. The same thing that I opened for you in the Excel that you are seeing here, right? So now what we are trying to do here now is we're now saying DS3 this drop name. We want to drop name. We want to drop this. This the name, the table name. So drop colon name. Drop the colon that has name. Drop the colon that has name, right? So let's run that. So can you see? If you see, we said drop the column that has name. So if you look at this DS updated one, the symbol is no longer there again, right? So now define our y variable. Our y variable is the features, the PIC50. So we are saying df3 underscore y equals to df3 PIC50. So we are extracting PIC50 from the df3. This particular data, this one, we are extracting is df3. So we are extracting what we are saying is Python go to df3, extract only the PIC50 only, and save it as df3 underscore y. So we have to define our x-axis and our y-axis. So this is our x-axis, y-axis. Our y-axis is the what? Is the PIC50, which is the label, right? I think we have another. Okay, so now that's good. So combining the x and the y-axis now. So I think so our x-axis is the descriptor now, right? Can you see? And then we've defined our x and we've defined our y-axis. So we have to combine the two now, right? So data set 3 equals to panda concatenate as combine our DFS, our x-axis and our y-axis with axis equals to 1. That means we should put this dx y, that's the PIC50, should be at the end, there, at the extreme end. So let's go back. Let me show you this. Can you see? So we've combined the y-axis, the PIC50, with our x-axis, the descriptor, right? So that we can now save this into a new data set. So save this data set 3 as mtb underscore o6 bar2 data. So we are saving it like that. So it saved that. So we already saved this now. So if you look at this, is going to appear error for us right now. So we already saved this. So next, by the time we start the next, then this is going to be the data we'll be working with. So any questions so far? Like I said, I don't want to rush this. That's what I'm doing. I separate it into, I think we should have like one or more parts, and we are done with the model. Yes, one or more parts. So, but what thing you will do for me, which I will encourage, is please take your time, right, to do this on your own. I can do this in 1 week or 2 weeks, but I decide not to do that because I want you guys to have, and I believe you guys are not having issue with it because nobody has ever come to me or to Dr. Scott and said, these two scripts we did last 2 weeks, I'm having problem with it. I want to believe you are working with it and you don't have any problem. That's why nobody is talking to me about anything. Okay, I want to believe that. So this has been saved now. Can you see? This has been saved. So once this has been saved, for you to be able to, this is on, like I said, it's on the cloud. You can download each of them. Just right click on it and click download. This is a folder. Yes, you can download each of them. Let me go to this. Yeah, or you click on this part, download each. You can download them. Right click, you can download each and every one of them. I think there's even a script I can use. There is a script I can use to download. Let me see. I don't know if I still have the script. I have it somewhere. Let me see. Yes, you can use this script to I think no, it's just to zip, not this script. Yeah, I will definitely find that for you guys. So what we've done now, we've put together our x and the y axis now. So the next thing is to go to our model building, right? So any questions so far? Any question, anybody that has any question that is something that is not clear? Or is there anything you want me to talk about again? No question, right? Okay, I want to believe there is no question. Okay, fine. Thanks. And I want to believe everything is clear. So this is going to help you. In fact, apart from this, I'm like still going to do something else to build a model, right? So this is going to help you to at least have understanding of how AI works, right? How it works, and this is just a step in model building, right? So please take time, run through it. As soon as I'm done now, the video will be available, and I'm going to send the script, this part 3 script, to everybody so that you can have something to work with. If you have any question, like I used to say, get in touch with me. I can run all this whole thing in 3 weeks, in 1 week, or in one class or 2 classes. But I decide to be doing it one by one, like I'm doing it now, so that you guys will have time to run through each. And I want to believe you guys are doing this. Even though nobody has come to me and said, Dr. Ken, I'm having this issue, I want to believe you are getting it. But don't forget this part 3, please use Google Colab to run it. I'm still going to figure out how we can run those few bash scripts on notebook. Maybe I will discuss with Dr. Scott too how we can sort that, so that you can just run everything from the beginning to the end on Jupyter Notebook without going to Google Colab. But for now, just run this particular part 3 on Google Colab. All right. Any question? And if there's no question, yeah, I think let's call it a day. Let's draw the curtain today. But I'm encouraging you. I know you have your classes that you are doing. Just spend 1 hour, 2 hours in 1 week on this, and it will really help you. All right. Thank you very much, guys. Have a great weekend.
Thank you very much. You as well.
Thank you, sir.
You're welcome, guys.